Imagine passing this um, sweeping, super well-intentioned law to protect children online, right?
Right.
The goal is obviously to keep them off addictive algorithms and shield them from bad content. But the direct, immediate engineering result of that law is that hackers suddenly get access to a centralized database containing the passports, birth certificates, and like real-time facial scans of 10 million teenagers.
Yeah, it's a complete disaster.
Welcome to the 2026 privacy paradox, everyone. It is the perfect illustration of how, well-meaning policy can create just catastrophic engineering realities.
It really is a profound structural failure. I mean, we are looking at an internet ecosystem that is basically tearing itself apart right now.
Because it's trying to reconcile two completely opposing forces.
Exactly. On one side, you have the world's absolute reliance on data-hungry tech, specifically AI. And on the other side, you have this incredibly aggressive, globally fragmented set of privacy laws trying to lock all of that data in a vault.
And the old methods, like it's clicking, I agree on some pop-up, they don't work anymore legally or technically. So welcome to this custom-tailored deep dive into the rapidly evolving 2026 data privacy landscape. I am thrilled you are joining us today.
Yeah, glad to be here and unpacking this with you all.
If you've been following the tech sector at all, you know the stakes have literally never been higher. We are analyzing a massive stack of source materials today, from deep legal analyses by firms like Fisher Phillips and Mayer Brown to these really complex technical white papers from the W3C and New America.
And our objective today isn't just to list a bunch of new laws. I mean, you can look those up. Our mission is to decode the actual mechanics of compliance.
Like the architecture you need to actually survive them.
Exactly. We're going to look at the operational nightmare of age verification, the massive liability around biometric data, and ultimately the mathematical breakthroughs that are being deployed right now to basically salvage the digital economy.
And before we get into that architecture, I do want to note that this incredibly detailed privacy deep dive is made possible by our sponsors, CISOmarketplace.com and www.microsec.tools.
They are fantastic platforms.
Truly. They're dedicated to empowering security professionals with the exact operational tools you need to navigate this maze we're about to explore. We also have a suite of privacy micro tools supported by them that we'll be referencing throughout the discussion today.
Which are going to be super helpful, trust me. So just to map out our journey for you, we will start by looking at the death of privacy theater and the new demand for verifiable back-end code.
Then we're going to dissect that children's privacy paradox we mentioned, right?
Yeah, and the explosive backlash against biometric tracking. From there, we'll look at the core conflict between AI's data hunger and data minimization laws before breaking down the cryptographic architectures that might just save us.
Okay, let's unpack this. We have to start by establishing the baseline of the current regulatory environment.
Right, which is chaotic.
Yeah, chaotic is the word. As of 2026, over 140 countries, covering roughly 82% of the global population, have comprehensive data privacy legislation in place.
It's massive.
And in the U.S., because we still don't have a unified federal framework, we just have this volatile patchwork. Over 20 individual states now have comprehensive consumer privacy laws fully enacted.
You've got the early adopters like California, Virginia, Colorado.
And now the new rollouts, right? Like Indiana, Iowa, Nebraska, Texas.
Exactly. But what's critical to understand about this patchwork isn't just the sheer volume of the laws, it's the fundamental shift in how they are being enforced.
Right.
We have officially transitioned from the era of privacy theater to the era of technical truth.
I want to stop on that phrase, technical truth, because for the last decade, compliance really was just theater, wasn't it?
Oh, absolutely.
I mean, a company's legal team would write a 50-page privacy policy, an engineer would just slap a consent banner on the front-end UI, and boom, everyone assumed they were compliant.
Yeah, the regulator would look at the website, see the banner, and just move on. It was a totally surface-level inspection.
Like checking the blueprints to see if you drew a fire escape, but never actually checking if the door opens.
That is a perfect analogy. But regulators, they've become significantly more sophisticated now. Like, look at the European Data Protection Board, the EDPB.
Right. They launched their 2026 Coordinated Enforcement Framework, the CEF.
Yeah, and that involves 25 different data protection authorities across Europe conducting synchronized, highly technical audits of major platforms. They aren't just reading your privacy policy anymore to see if the legal terminology is sound.
No, they are demanding to see the database schema. They want to know exactly how the front-end UI maps to your back-end infrastructure.
Exactly.
I was actually looking through the EDPB's methodology, and they are rigorously testing things like suppression lists and auto-deletion scripts.
Yep, they want proof.
right? Like if your policy says we retain user data for 30 days, they don't just take your word for it. They want an engineer to sit down and show them the automated CR on job or the database trigger that actually purges that specific row of data from your AWS servers on day 31.
And if that automated protocol fails, or if it leaves even a trace of residual data in some forgotten backup server, that is an enforcement action right there.
Wow.
Yeah, fines are now heavily targeting the mechanics of consent. Under the GDPR, Article 6 violations, which govern the lawful basis for processing data, those now account for 1/3 of all enforcement penalties.
They are literally looking at the logic gates in your code.
They are. Take the Global Privacy Control, the GPC, as an example.
Oh man, the GPC is such an engineering headache.
Right. The concept is great for users. You set a universal preference in your browser that says, do not sell my data, and every website you visit has to automatically honor it without showing you a pop-up banner.
But from an engineering standpoint, honoring that is just a nightmare. The browser sends the GPC signal as an HTTP header, right?
Yeah, the SEC GPC, one header.
Right. But the problem is, the moment a user hits a web server, that server is already initiating, like dozens of asynchronous calls to third-party ad networks, analytics providers, content delivery networks.
Instantly.
So by the time the server actually parses that GPC header, the data might already be in flight to a third-party vendor.
Exactly. So an auditor is now coming in and asking, show me the latency in your consent propagation.
How do you guarantee the signal halts the API call before the page even renders?
You have to prove it. It requires this incredibly synchronous, unified consent management architecture that sits in front of the entire data layer.
Which most mid-sized companies just do not have.
They don't. And regulators are also aggressively penalizing dark patterns now. They're actually analyzing the CSS and the user flow.
To see if the platform intentionally manipulated the user. Right.
Yeah.
Like making the accept all button massive and bright green.
Yeah, and hiding the reject all button behind a tiny, low-contrast hyperlink. Regulators now possess the technical authority to declare that consent legally invalid because it was gathered deceptively.
I should note really clearly for you listening, these regulatory frameworks stem from incredibly diverse political and cultural priorities around the globe.
Very much so.
And in this deep dive, we're absolutely not taking a stance on the politics of the policies themselves. Both left-wing and right-wing governments are pushing various aspects of this.
Right, we're strictly looking at the engineering impact.
Exactly. We are just impartially reporting on what the source material says is happening to the tech landscape. And if you are trying to map these rapidly changing operational requirements yourself, privacyrights.compliancehub.wiki is an excellent micro tool to keep bookmarked.
It's highly necessary because the compliance burden is monumental.
And that's exactly where I want to push back a bit. We're talking about dynamic consent propagation, architectural level audits. Is it even possible for a mid-market company to comply with 140 different national laws and 20 different U.S. state laws all at the same time?
Honestly, it's incredibly difficult.
If Texas requires one specific data handling protocol and the EU requires something that directly contradicts it, how does a centralized database handle that routing?
It generally forces companies into one of two architectures. Either they adopt the strictest possible global standard, usually the GDPR or the CCPA, and just apply it universally to their whole user base.
Which totally hurts their monetization in less regulated markets.
Right. Or they have to build these incredibly complex IP-based jurisdictional routing engines.
Or the app dynamically alters its data collection behavior based on where the user's connection is coming from.
Exactly, which introduces massive latency and infrastructure costs. And this friction brings us to basically the most volatile area of the entire privacy landscape right now.
The children's privacy issue.
Yes. The ultimate example of how these conflicting mandates create impossible engineering scenarios.
The digital safety of minors has basically become the defining regulatory battleground of 2026. We are witnessing an unprecedented global crackdown.
It's everywhere. In the winter of 2025, Australia implemented a blanket social media ban for users under the age of 16.
And then the UK, France, Denmark all rapidly pursued similar strict age gating requirements.
And it is heavily impacting the U.S. too. We have 25 states that have enacted or introduced severe age verification laws restricting minors.
On top of that, the California Consumer Privacy Act, the CCPA, was amended to automatically classify any data belonging to a user under 16 as sensitive personal information.
Which triggers a whole different, much higher tier of encryption and handling requirements.
And we have to mention Brazil's digital ECA framework that took effect in March 2026. It explicitly bans behavioral profiling and targeted advertising for minors on any platform likely to be accessed by children.
Notice that phrasing. Not just platforms designed for kids, like a cartoon app. Any general-purpose platform a child might realistically use,
Which is essentially the entire internet.
basically.
But here's the critical engineering problem. If a platform is legally mandated to ban anyone under 16, or if they're legally barred from serving a targeted ad to a 15-year-old under threat of massive fines, that platform can no longer operate on assumption.
No, they have to possess what the laws call actual knowledge of the exact age of every single user hitting their servers.
And that completely destroys the old model of self-declaration. The web form asking, please enter your birth date, or a little checkbox stating, I confirm I am 18.
Regulators just laugh at that now. Bad actors and children themselves, they just lie.
So to achieve actual knowledge, platforms have to implement robust, verifiable age gating, which means they have to integrate with third-party identity providers.
And this is where it gets scary.
A user tries to create an account, and the platform says, stop. Upload a high-resolution photo of your government-issued driver's license or passport, and then turn on your webcam and let us run a real-time 3D facial biometric scan to prove you are the person in the ID.
This is the privacy paradox in its absolute purest form.
It really is.
The legislative intent is to protect children from the harms of social media. But the operational reality is that lawmakers are inadvertently forcing consumer tech companies to build massive, centralized honeypots of the most sensitive, immutable personal data imaginable.
Let's talk about the architecture of a honeypot, because from a cybersecurity perspective, this is a nightmare.
A total nightmare.
If I'm running a standard messaging app, my database schema used to just contain an encrypted password hash and a phone number. If I got breached, it was bad, but the blast radius was limited.
Right, you just reset the password.
Exactly. But now, because of these age verification laws, my database has to store API tokens linked to biometric facial maps and parse data from government IDs. I have just painted a massive target on my infrastructure for every ransomware syndicate on the planet.
And it fundamentally violates the core tenet of modern data protection, the principle of data minimization.
Which says you should only collect the absolute minimum amount of data strictly necessary to provide the service.
Exactly. A messaging app does not need your passport to transmit a text message. But the law mandates the collection.
And if that honeypot is breached, attackers aren't just getting emails. They are getting the immutable biometric markers of millions of minors. You cannot reset a facial structure.
No, you can't. And we are seeing very different architectural philosophies globally on how to mitigate this. Our sources highlight a really sharp contrast between the UK and Australia versus California.
Walk us through that.
Well, in the UK and Australia, the regulatory burden of verifying age is placed directly on the individual service providers and app developers.
Which means virtually guaranteed overcollection. Like, if I download 50 different apps, 50 different servers are independently prompting me to verify my identity.
Yes.
So my data is being fractured and stored across 50 different vendor ecosystems, any one of which could have a compromised server.
It expands the attack surface exponentially. It's reckless. California, conversely, recognized this architectural flaw and passed the Digital Age Assurance Act, taking effect in 2027.
And that framework shifts the verification burden away from the app layer, right?
Yeah.
Down to the operating system or app store level.
Exactly. The concept is centralized verification with decentralized trust.
How does that work in practice?
When you buy a smartphone and set up your core OS account, the OS provider like Apple or Google, they perform the robust age verification once. They verify the passport or biometric data locally within their highly secured infrastructure.
Okay, so it stays on the device.
Mostly, yes. Then, when you download a third-party app, the OS simply passes a cryptographically signed token to the app.
So the token just contains a Boolean value. It literally just says over 16 equals true.
Exactly. The third-party app developer is legally permitted to accept that token as actual knowledge of the user's age. The app never sees the passport, never runs the facial scan, and never knows the exact date of birth.
It contains the blast radius.
It does.
It's an elegant solution. But, it still relies on the device manufacturer hoarding that biometric data in the first place, which is still a single point of failure.
That's true, but it's vastly better than 50 random startups holding it.
Fair point. If you want to track how these highly volatile compliance rules around minors are shifting, childrenprivacylaws.com is a vital resource for that. But this discussion of operating systems running facial scans perfectly transitions us to the broader explosion of biometric tracking.
Oh, the aggressive regulation of biometric data is easily one of the most defining legal trends of 2026.
For sure.
As biometric primitives, facial recognition, iris scanning, voice printing, gait analysis, as those have moved out of high-security government facilities and into everyday consumer hardware, the regulatory pushback has been severe.
It is genuinely surprising to me that the U.S. still lacks a cohesive federal biometric privacy law. We're relying entirely on the states right now.
Yeah, it's a bit of the Wild West.
For a long time, the landscape was just dominated by the Illinois Biometric Information Privacy Act, BIPA, which allowed for those massive class action lawsuits. But now the net is widening. Colorado just enacted the Biometric Data Privacy Amendment.
And the Colorado Amendment is highly specific. If an organization captures biometric data there, they cannot just bundle the consent into their general terms of service.
All right, they need standalone consent.
Yes, and they must maintain a publicly available retention schedule, deploy automated destruction protocols the moment the purpose of the data collection is fulfilled, and have specific incident response plans solely for biometric breaches.
Texas also rolled out the Responsible Artificial Intelligence Governance Act this year. It prohibits AI systems from capturing biometric identifiers without express affirmative consent.
But as stringent as the U.S. state laws are becoming, they pale in comparison to the European Union. The EU AI Act is monumental.
Let's dig into that because the EU AI Act categorizes AI systems by risk, right?
It does, and it outright bans certain biometric practices, declaring them an unacceptable risk to fundamental rights. For instance, it entirely prohibits untargeted facial scraping from the internet.
So a company can no longer deploy web crawlers to just download millions of public social media photos, extract the facial geometry, and train a proprietary model.
That practice is now explicitly illegal in the EU, period. Furthermore, they have banned the use of AI systems designed to infer emotions in workplace and educational settings.
I really want to dig into the mechanics of that. I read about the ban on emotion inference, but how does an auditor actually define that in code?
It's tricky.
All right, let's say I build video conferencing software, and I write an algorithm that tracks a user's eye movements solely to keep the camera focused on their face, or to automatically blur the background when they shift in their seat.
Okay.
Does an EU regulator misinterpret that computer vision model as cognitive tracking or emotion inference?
That is the exact friction point corporate legal teams are fighting over right now. The EU defines emotion inference as an AI system that attempts to identify or infer the emotions or intentions of natural persons on the basis of their biometric data.
So how do you defend your camera focusing app?
The defense relies on proving the mathematical intent of the model. If your computer vision model only maps spatial coordinates, literally just the X and Y axis of the pupil to adjust a digital bounding box, that is permissible.
This is just geometry.
Exactly. But if the model correlates a widened pupil and a specific micro-expression in the jawline to output a data label of frustrated or disengaged on some boss's employee dashboard, you are in direct violation of the act.
Wow. It is a razor-thin line between spatial mapping and behavioral profiling.
Very thin. And the EU has also heavily restricted real-time remote biometric identification by law enforcement in public spaces.
Right, with extremely narrow exceptions, like searching for a specific missing child. The default stance is prohibition.
Correct.
But on top of the corporate tracking and government surveillance, we also have to talk about the malicious weaponization of biometrics, deepfakes.
Yeah, this is huge.
The federal Take Eye Down Act takes effect in the U.S. in May 2026. This legislation criminalizes the publication of non-consensual intimate imagery, NCII, and AI-generated deepfakes.
And it mandates a strict 48-hour takedown window for platforms once they receive a verified report. The penalties are uncompromising.
Up to 2 years in federal prison for adult offenses, right? And 3 years for minors.
Yes, but the operational burden on the platforms is just immense.
Let's look at the operational reality of that 48-hour window. A user reports a deepfake video. A human moderator or an AI classifier reviews it, confirms it violates policy, and deletes the video file from the server.
Simple enough, right?
Right. But under the Take It Down Act, the platform also has to take reasonable steps to prevent that identical video from just being re-uploaded by a different bot 5 minutes later. How do they mathematically block a file they don't even have anymore?
They rely on hashing databases. Before deleting the malicious video, the platform runs it through a hashing algorithm to generate a unique digital fingerprint, a hash of that specific file.
And they store that hash in a suppression database.
Exactly. Every time a new video is uploaded globally, the system hashes the new file and compares it against the suppression database. If the hashes match, the upload is automatically blocked at the server level.
But bad actors know exactly how this works. If a platform is using a standard cryptographic hash, like SHA-256, all the attacker has to do is alter a single pixel in the deepfake video.
Just one pixel.
They add a tiny, invisible watermark, or slightly adjust the color grading. That tiny alteration completely changes the resulting SHA-256 hash. System won't recognize it, and the video just gets uploaded again.
Which is exactly why platforms are forced to deploy highly complex perceptual hashing models, like photodNA or specialized neural hashes.
How do those differ?
Unlike cryptographic hashes, which change completely if one byte is altered, perceptual hashes analyze the visual features of the image, the contrast, the shapes, the actual structural content.
Oh, interesting.
Yeah, so even if the attacker resizes the video or adds a filter, the perceptual hash remains similar enough to trigger a match and block the re-upload.
It's basically an endless arms race between adversarial AI generators and perceptual hashing classifiers.
Pretty much.
If you were navigating this highly technical, legally fraught landscape of physical data, biometric.myprivacy.blog is an excellent resource to track the compliance requirements.
Highly recommend checking that out.
But, all of this heavy restriction brings up a massive fundamental contradiction. We are cracking down on facial scraping. We are passing laws demanding extreme data minimization, restricting how biometric data can be processed. So how on earth is artificial intelligence surviving?
That is the defining technological conflict of this decade.
AI data hunger versus data minimization.
Exactly. The insatiable data hunger of AI models versus these incredibly strict legal mandates.
Because AI models, especially large language models and generative multimodal systems, they require incomprehensible amounts of data to train effectively.
Terabytes upon terabytes.
They need to ingest human interaction, medical records, financial transactions, visual media to find the statistical patterns that actually make them useful. But the laws are explicitly saying you can only collect what is strictly necessary for a specific immediate transaction, and you must delete it as soon as that transaction concludes.
These two realities are perfectly opposed.
They are.
And the stakes for getting the balance wrong are existential for businesses because customer PII, personally identifiable information, remains the absolute #1 target for cyber attacks.
Attackers aren't necessarily looking for proprietary source code anymore.
No, they want names, social security numbers, dates of birth, financial routing data. They sell it on the dark web or use it for identity fraud. The 2025 IBM Security Report highlighted that the average global cost of a data breach hit a record $4.88 million.
And in highly regulated sectors like healthcare, the average cost is a staggering $7.2 million per incident.
So you have these pharmaceutical companies, financial institutions, tech giants with these massive, incredibly valuable data sets. They desperately want to feed this data into AI models to predict market trends or accelerate drug discovery.
But legally, those data sets are ticking liability bombs.
Exactly. And it is critical here to distinguish between security and privacy, because our sources emphasize that security alone is no longer a defense.
What's the practical difference there?
Security focuses on protecting data from unauthorized external access. It's building a thicker, higher wall around your servers to keep the hackers out. Privacy, however, governs how that data is lawfully collected, analyzed, and shared by the authorized personnel inside the wall.
Ah, right. So you can have a perfectly secure database that is completely illegal under the GDPR because you didn't have the proper lawful basis to process the data in the first place.
Exactly. And the standard industry response for years has just been de-identification.
Right, like a hospital wants to train an AI to detect early onset Alzheimer's. They take a database of 100,000 patient records, and they just strip the name and social security number columns off the spreadsheet before feeding it into the neural network.
They claim the data is anonymous.
But that doesn't actually work anymore, does it?
No, it completely fails. True, irreversible de-identification of rich data sets is mathematically incredibly difficult, if not impossible, against modern computational power. The real risk lies in inference attacks, also known as re-identification attacks.
I want to break down exactly how an inference attack works, because it sounds like a parlor trick until you see the math.
Let's do it.
Let's say you have that anonymized medical database. It doesn't have names, but it still contains the patient's gender, their zip code, their date of birth, and the specific dates they visited the hospital for a broken leg.
Those are known as quasi-identifiers. Individually, they don't identify anyone.
Right. But an attacker, or an AI model, takes that anonymized hospital data set and cross-references it with a completely different public data set. Let's say voter registration records, which include names, zip codes, and dates of birth.
Or even just scraping a public social media feed.
Right. The AI looks for the overlapping matrices. The algorithm cross-references the quasi-identifiers. It calculates that in this specific zip code, there are only 12 males born on this specific date.
And then it correlates that with the hospital visit.
If only one of those 12 men visited the emergency room on a specific Tuesday, and that same man posted a public picture of his leg in a cast on social media on that same Tuesday, the AI has achieved a 100% probabilistic match.
The AI pieces the puzzle back together. It mathematically proves that patient #4599 in the anonymous medical database is undeniably John Doe.
And suddenly, John Doe's entire private medical history is exposed.
That is the sheer danger of high-dimensional data. The more data points you have, the more unique every individual's statistical fingerprint becomes. Organizations are trapped in a vice right now.
They have a strict legal mandate to protect privacy, but a massive commercial imperative to maximize data injection for AI training. If you need to understand how to properly classify, audit, and protect that highly targeted PII within your architecture, pii.compliancehub.wiki is the resource you need.
Definitely.
But this brings us to the core question, the ultimate cliffhanger here. If de-identification fails against inference attacks and data minimization laws prohibit hoarding raw data, how do tech companies and researchers actually solve this impossible puzzle?
How do they use the data without looking at it?
Exactly. How do they train the AI without legally being allowed to see the raw info or risking exposure in a breach?
They don't solve it with better firewalls or longer privacy policies. They solve it with advanced mathematics. Specifically, they're deploying an arsenal of cryptographic architectures, collectively known as privacy-enhancing technologies, or PETs.
PETs.
Yes, and this is a booming market, projected to be worth $42.7 billion by 2035.
This is the master key for the next decade of software engineering.
It is a complete paradigm shift. For decades, the goal of data security was hiding data. PTs represent a shift toward mathematically proving privacy.
Okay, what does that mean in practice?
They are a diverse set of cryptographic methodologies designed to either obscure the data mathematically or facilitate the extraction of insights without ever revealing the raw underlying inputs. They allow you to get the value out of the data without ever exposing the personal information to the analyst or even to the AI itself.
Let's do a deep dive into the mechanics of these specific PETs, because the concepts challenge our basic understanding of how computing works. Let's start with differential privacy.
Great place to start.
We touched on inference attacks earlier. Differential privacy is specifically designed to stop them, right?
Yes. Differential privacy is not an encryption algorithm, actually. It is a mathematical framework that provides formal, quantifiable privacy guarantees. It works by injecting controlled, random statistical noise into a data set or into the query results generated from that data set.
So instead of trying to perfectly strip identifiers, you purposefully corrupt the data just enough to hide the individual, but not enough to ruin the big picture trend.
Precisely. It typically utilizes a Laplacian or Gaussian distribution to add this noise. The goal is to ensure that the final output of any statistical analysis is virtually indistinguishable whether any specific individual's data is included in the dataset or not.
If the output doesn't change based on your presence, an attacker cannot infer anything about you. The concept of the privacy budget, or the epsilon value, is fascinating here. It's an actual mathematical equation balancing utility and privacy.
Yes, epsilon is the tunable parameter. If an organization sets a high epsilon value, they are injecting less noise.
So the data retains high utility and analytical accuracy.
Right, but the privacy guarantee is weaker. If they set a low epsilon value, they inject massive amounts of noise. The privacy guarantee is ironclad, but the resulting data might be too statistically skewed to be useful for precise AI training.
It is a constant calibration. The U.S. Census Bureau actually used differential privacy for the 2020 census.
They did, yeah.
They had to publish demographic trends for redistricting, but they were legally barred from releasing data that could identify a specific household, so they added mathematical noise to the block-level data. Apple and Google also use local differential privacy extensively, don't they?
They do. When your phone sends usage statistics back to their servers, like what emojis are most popular or what words you frequently misspell, the phone adds noise locally before it ever transmits the data.
The server receives a chaotic mess.
Right, but when it aggregates millions of chaotic messes, The noise mathematically cancels out, and the true statistical trend emerges.
It is highly effective for aggregate statistics. But differential privacy does not allow you to perform precise calculations on specific individual records.
No, it doesn't.
When you need to do heavy, exact mathematics on highly sensitive data like training an AI model on a specific patient's genome in a public cloud, you need homomorphic encryption.
Homomorphic encryption, or HE.
This is the concept that I've always thought sounded like actual science fiction.
It definitely challenges conventional logic. Homomorphic encryption is a family of cryptographic schemes that allows complex computations to be performed directly on encrypted data without ever requiring the data to be decrypted first.
Wait, I really want to visualize this architecture.
Yeah.
Traditionally, if I store an encrypted file on an AWS server, and I want AWS to run a machine learning algorithm on it, the server has to decrypt the file using a key, hold the raw plaintext data in its memory registers, run the math, and then re-encrypt the answer.
That is the traditional vulnerability window, yes. Data in use.
During that processing window, the data is totally exposed to anyone who breaches the server.
Exactly. But with homomorphic encryption, you encrypt a file on your local machine, you upload the ciphertext, the encrypted gibberish, to the cloud.
Okay.
The cloud server's AI model performs complex polynomial algebra directly on the ciphertext itself. The server never has the decryption key. It never sees the raw data.
It just does math on the gibberish.
Yes. It generates an answer, which is also encrypted ciphertext. It sends that encrypted answer back to you, and you use your local key to unlock it and see the result.
The cloud provider mathematically processes the data while remaining totally blind to what the data actually is.
That is exactly how it functions. It relies on complex lattice-based cryptography. It preserves the structural properties of the data even while encrypted, allowing algebraic operations like addition and multiplication to cascade through the ciphertext and produce a valid encrypted output.
It is miraculous. But I have to ask about the latency. I know that historically, the computational overhead for HE was catastrophic.
Oh, it was awful.
Performing fully homomorphic operations on structured data could take thousands of times longer than processing plain text. It was theoretically brilliant, but practically useless for commercial enterprise. What changed?
Hardware acceleration caught up to the mathematics. This is the big breakthrough for 2025 and 2026. The major silicon manufacturers realized that software-level optimization just wasn't enough.
So what did they do?
Intel introduced Trust Domain Extensions, TDX. AMD released Secure Encrypted Virtualization, SEV.
These are capabilities built directly into the physical server processors.
Yes. They provide hardware-level memory encryption. The CPU itself isolates and encrypts the memory registers used for these specific workloads. By moving the cryptographic processing down to the silicon level, they have reduced the performance penalty of these secure workloads by 40 to 60%. Furthermore, we are seeing the emergence of dedicated, application-specific integrated circuits ASICs designed solely to accelerate homomorphic encryption. These specialized chips can process terabits of encrypted data per second.
Because of this massive hardware evolution, HE is now commercially viable for enterprise AI training for the first time.
Exactly. So a hospital can confidently upload patient oncology records to a public cloud, run a massive predictive AI model on them, and confidently tell regulators, even if the cloud provider is fully compromised by a nation-state actor, the hackers stole nothing but unbreakable, mathematically useless noise.
And that capability directly enables another powerful P, secure multi-party computation, or SMPC, and its critical subset, private set intersection, or PSI.
Yes, I love the architecture of private set intersection.
Let's walk through a real-world scenario of how this solves a massive cross-jurisdictional problem. Let's say the FBI and a major commercial bank want to collaborate.
It is the perfect use case for PSI. You have two entities that possess highly sensitive databases. They want to find the overlapping data points, the intersection, but they are legally and competitively prohibited from exposing their full databases to each other.
Right. The FBI has a classified watch list of 10,000 suspected money launderers. The commercial bank has a database of 5 million customer accounts.
The FBI wants to know if any of their suspects hold accounts at this specific bank.
But the bank cannot legally hand over the financial records of 5 million innocent citizens to the government without a warrant. And the FBI absolutely cannot hand over a highly classified ongoing investigation watch list to a private corporation. They are at a complete stalemate.
Traditionally, yes. But using private set intersection, they engage in a secure cryptographic protocol. They both encrypt their datasets using commutative encryption algorithms. They exchange the encrypted sets and perform a mathematical comparison.
And because it's commutative, the order of encryption doesn't matter, allowing them to find matches in the ciphertext.
Precisely. The mathematical output of this protocol will only reveal the exact elements that appear in both sets. So the protocol concludes, and the output reveals three specific names.
The FBI learns absolutely nothing about the other 4,999,997 innocent customers at the bank.
And the bank learns absolutely nothing about the other 9,997 suspects on the FBI's classified watch list.
The legal and competitive risk of collaboration drops to zero. Rival financial institutions form consortiums using SMPC to track organized fraud rings. They can check if the same synthetic identity is applying for loans at 5 different competing banks simultaneously, without any of the banks having to expose their proprietary customer lists to their competitors.
It is a massive breakthrough for insight sharing. And we must also look at how data is secured physically on the device itself, which brings us to trusted execution environments, or TEEs.
TEEs are fascinating because they provide a hardware root of trust. Explain the hypervisor isolation here.
A TEE is a dedicated, physically isolated area on a processor, whether that is a smartphone chip or a cloud server CPU. It operates independently from the main operating system. It has its own isolated memory and execution space.
It's like a heavily armored vault inside the computer.
Yeah.
And the critical point is that even the system administrator, or the root user of the main operating system, cannot look inside the TEE while it is processing data.
Correct. Even if a highly sophisticated malware variant completely compromises the main OS, it cannot breach the hypervisor layer, isolating the TEE.
So how does data get processed?
The data goes into the TEE encrypted. The TEE decrypts it internally using keys securely stored within the enclave, performs the processing, re-encrypts the output, and sends it back to the main system.
But I have to push back on the perfect security of enclaves. Haven't cybersecurity researchers demonstrated side-channel attacks against TEEs?
They have, yeah.
Where they don't actually breach the enclave, but they measure the power consumption or the electromagnetic emissions of the chip while it processes, and use that physical data to reverse engineer the encryption keys.
That is a highly sophisticated and valid critique. Side-channel vulnerabilities, like power analysis or timing attacks, have historically been the primary threat vector against TEEs.
So are they safe?
Yes, because the 2025 and 2026 iterations of hardware enclaves, like AWS Nitro enclaves and the latest ARM and Trust Zone architectures, have implemented massive mitigations against side-channel leakage, including randomizing execution times and heavily shielding power profiles. For commercial applications, they remain the gold standard for secure processing.
This is exactly how smartphone biometric unlocks function, isn't it? When a user sets up Face ID or a fingerprint scanner, that highly sensitive biometric template isn't just sitting in the phone's general flash memory where a rogue app could access it.
No, it is generated and permanently locked inside the device's TEE. When you attempt to unlock the phone, the camera sensor sends the real-time image data directly into the TEE. The main operating system never sees the raw image.
The TEE compares the real-time image against the stored template.
Exactly. The OS simply waits at the gate and asks the TEE, is this the authorized user? The TEE processes the match internally and simply returns a Boolean output to the OS. Yes, unlock, or no, deny.
The raw biometric data never leaves the hardware enclave. And that localized processing concept ties perfectly into the final major piece we need to discuss, which is specifically revolutionizing AI, federated learning.
Federated learning fundamentally inverts the traditional machine learning architecture.
Because historically, AI training relied on massive data centralization.
Yeah, you pull all the raw data from millions of smartphones or hospital servers, pool it in a central cloud data lake, and train the master model.
But as we discussed, that violates data minimization and creates a massive honeypot.
Right, so federated learning leaves the data exactly where it is.
The raw, localized data never leaves the edge device.
Yes. Instead, the central server sends a copy of the AI algorithm down to the edge device, the smartphone, the local hospital server, the IoT sensor.
The algorithm travels to the data, not the data to the algorithm.
Exactly. The local device trains its local copy of the model using its own localized data. Through a process called stochastic gradient descent, the model learns the statistical patterns locally.
And then what?
Then the local device takes only the learned parameters, the mathematical weights and gradient updates, not the raw data, and transmits those back to the central server. The central server aggregates these mathematical updates from millions of decentralized devices to improve the global master model.
It learns from the crowd without ever looking at anyone's personal diary. That is brilliant architecture.
Before we move to the final applications, it is worth clarifying two foundational data obfuscation methods that often support these broader P8 architectures: hashing versus tokenization.
They are frequently conflated, but functionally very different. Our sources from New America provide an excellent analogy for this that cuts through the cryptography.
I love this analogy.
Hashing is like blending fruit into a smoothie. It is a one-way, mathematically irreversible process. Once you blend a strawberry, a banana, and an apple to a smoothie, you can never extract the whole strawberry back out.
Right. You can taste the strawberry, meaning you can verify the data was present, but the original form is permanently destroyed.
Exactly. A cryptographic hash function takes an input of any size and produces a fixed size string of characters. It is deterministic. The same input always produces the exact same hash.
It is primarily used for integrity verification. When a database stores your password, it doesn't store the actual word, it stores the hash. When you log in, it hashes the password you typed and compares the two hashes.
The system verifies you know the password without ever needing to know what the password actually is.
And tokenization is fundamentally different. Tokenization is like a gym membership card.
Right, when you join a high-end gym, they don't print your name, your home address, and your credit card number directly on your plastic ID badge.
They give you a badge with a random, meaningless string of numbers. A token. If you drop that badge on the street, it is completely useless to whoever finds it. It contains no intrinsic value.
But when you scan that token at the gym's front desk, their highly secured internal database matches that token back to your profile and bills your credit card.
That is the crucial distinction. Tokenization is reversible, but only by the specific entity that holds the secure vault mapping the token to the raw data. It is heavily used in payment processing and healthcare to allow systems to route data without exposing the underlying PII to the intermediate networks.
So we have explored this incredible arsenal of cryptographic architectures,
Yeah.
differential privacy, homomorphic encryption, secure multi-party computation, trusted execution environments, and federated learning.
It's a lot of math.
It is. We need to bring this deep dive full circle. How do these abstract mathematical concepts actually solve the massive real-world regulatory problems we discussed in sections 2 and 3?
Right. How do PTs solve the children's privacy paradox and the liability of biometric verification?
Yeah.
They solve it by completely decoupling the concept of identity verification from the act of data collection. And they achieve this primarily through the integration of zero-knowledge proofs and decentralized identifiers.
Let's break those down mechanically. Zero-knowledge proofs, or ZKPs. The concept sounds like a logical impossibility. How can I prove I know something without showing you the proof?
A zero-knowledge proof is a cryptographic protocol that allows one party, the prover, to mathematically demonstrate to another party, the verifier, that a specific statement is true without revealing any supplemental information whatsoever beyond the sheer validity of that specific claim.
The classic analogy is the colorblind friend.
Oh yeah, explain that one.
If you have a friend who is totally colorblind and you hold up a red ball and a green ball, they think the balls are identical. You want to prove to them that the balls are different colors, but you can't just tell them this one is red because they can't verify that. So you give them the balls. You tell them to put them behind their back and either switch hands or keep them in the same hands and then show you. Because you can see color. You can instantly tell them if they switched the balls or not.
And they can verify if you are right.
Exactly. If they do this 50 times and you get it right every single time, you have mathematically proven to your friend that the balls possess a distinguishing characteristic color without ever actually revealing to them what the colors are.
That is a highly accurate conceptual model. In a digital architecture, it relies on complex cryptographic challenges and responses. Apply this to the age verification paradox we discussed earlier.
The law mandates that a social media platform must have actual knowledge that a user is over the age of 16, but the user refuses to upload their passport and create a honeypot vulnerability.
Right. Using a ZKP, the user's device can engage in a cryptographic challenge with the platform server. The device mathematically proves that the date of birth associated with the user's verified identity falls within the required range, greater than 16 years ago.
And the platform receives a cryptographic Boolean output, a verified true.
The principle of selective disclosure. The platform achieves its legally mandated actual knowledge of the age requirement, but it never learns the user's actual date of birth, their name, their address, or sees an image of their government ID.
But how does the platform trust the math? The math has to be anchored to a real-world identity at some point.
Which brings us to the W3C's architecture for decentralized identifiers, or DDs, and verifiable credentials. This is the critical infrastructure layer.
How does that work?
Under this model, a trusted, authoritative issuer, such as a government department of motor vehicles, verifies your identity once, in person. They then issue you a digital verifiable credential.
But they don't store it on a central server.
No, they issue it directly to a secure, cryptographically locked wallet on your personal edge device.
So when a website prompts me for age verification, I don't send them the credential. I use the verifiable credential held in my local wallet to generate the zero-knowledge proof locally on my phone's processor.
Yeah.
I only transmit the generated proof to the website.
Correct. And the website, acting as the verifier, can examine the cryptographic signature attached to that proof. They can mathematically verify that the proof is mathematically sound, that it hasn't been tampered with, and that it originated from a credential issued by a trusted entity like the DMV without ever seeing the raw credential itself.
It solves the paradox beautifully. The platform complies with the regulation, but data minimization is perfectly preserved because no sensitive data was ever transmitted or collected.
There is no honeypot for hackers to breach.
But I have a major architectural question here. If the website is verifying the signature of the DMV credential, doesn't it have to ping the DMV's server via an API call to ask if the signature is valid?
That is a critical vulnerability known as phoning home, and the W3C standards are explicitly designed to prevent it.
Because if the website pings the DMV every time I verify my age, the DMV suddenly has a real-time surveillance log of every website I visit, every digital bar I enter, and every app I download. It creates a centralized tracking nightmare for the government.
Precisely. To prevent phoning home, the architecture utilizes decentralized registries or public ledgers. When the DMV issues the credential, they publish the public key associated with their issuing authority to a decentralized ledger.
They do not publish any user data.
Exactly. When the website needs to verify your proof, they check the cryptographic signature against the public key on the decentralized ledger.
They don't talk to the DMV. They talk to the math on the ledger.
Yes. The verifier authenticates the credential autonomously. The original issuer remains completely blind to how, when, and where the credential is being presented.
That's brilliant.
This architecture is further reinforced by the W3C concept of herd privacy.
Herd privacy, hiding in the crowd.
Exactly. Even if interactions are encrypted, metadata can leak identity. If your device transmits a cryptographic proof that is 5 kilobytes larger than everyone else's, that discrepancy acts as a tracking fingerprint.
So how do you fix that?
Herd privacy mandates strict standardization. Every cryptographic interaction is padded to standard lengths, utilizes standardized latency protocols, and employs uniform connection settings. Your digital footprint becomes mathematically indistinguishable from millions of other users. You achieve profound privacy at a structural architectural level.
The commercial opportunities unlocked by these architectures are staggering. We are moving from a paradigm of data hoarding, which is incredibly legally dangerous, to a paradigm of secure insight sharing.
It changes everything.
Pharmaceutical companies can pool insights on rare diseases across borders without ever exposing proprietary patient records or violating IT. Telecommunication providers and financial institutions can aggressively hunt down transnational fraud rings together in real time, securely computing overlapping threats without ever sharing their raw customer lists.
It fundamentally rewrites the rules of data governance. The ability to collaborate securely across organizational and sovereign boundaries without triggering the devastating penalties of the GDPR or the CCPA is the exact reason the PEACE market is experiencing such explosive growth.
And for the developers, the software architects, and the CTOs listening to this, who are inspired by these mathematical breakthroughs and want to integrate these privacy-preserving tools into their own infrastructure, I have a fantastic announcement.
Oh, this is great.
Our sponsors have just released a powerful new product, build.cyberdx.network. It is a comprehensive platform designed specifically for developers wanting to build out their own solutions using these advanced cryptographic primitives and DID architectures. I highly recommend checking it out.
Integrating these capabilities is no longer a niche security research project. It is an essential capability for the next decade of commercial software development.
As we synthesize this extensive journey, we began by analyzing how the legacy world of privacy theater is dead. Regulators are conducting code-level audits demanding technical truth and dynamic consent architecture.
We examine the severe operational paradoxes created by laws meant to protect children and restrict biometrics, observing how traditional compliance forces companies to build highly dangerous honeypots of sensitive identity data.
And ultimately, we found the resolution in mathematics, privacy-enhancing technologies like homomorphic encryption, federated learning, and zero-knowledge proofs that allow us to mathematically prove compliance while operating entirely on obscured data.
It represents a fundamental evolution in how we view digital architecture. Organizations must critically evaluate their data pipelines. Are you still relying on outdated privacy theater? Are you unnecessarily ingesting massive amounts of highly toxic PII simply to verify a basic Boolean requirement?
The cryptographic tools now exist to achieve verifiable technical truth, to train complex AI models securely, and to verify human identity without ever compromising personal privacy.
Investing in PETs is no longer just a defensive security measure. It is a critical business enabler in a hyper-regulated global market.
Before we sign off, I want to pivot. You always have a way of looking around the corner and seeing the unintended consequences of new technology. What is the next big tension? What is the provocative thought we should be mulling over as these technologies become ubiquitous?
It is a chilling but fascinating philosophical and technical dilemma. We have spent this entire deep dive analyzing how to perfect privacy using mathematics. But consider the end state.
Okay, what is the end state?
If privacy-enhancing technologies like zero-knowledge proofs, homomorphic encryption, and fully decentralized anonymous identifiers achieve their goal and become perfectly mathematically unbreakable, yes, we successfully protect global citizens from corporate surveillance and data breaches.
Right.
But do we also inadvertently engineer the perfect, impenetrable dark web?
Oh, wow. The ultimate double-edged sword.
If a protocol uses hardware-accelerated math to guarantee absolute, unbreakable privacy, that guarantee applies to everyone on the network equally. It protects the whistleblower, the investigative journalist, and the political dissident.
But it also provides an impenetrable shield for money laundering syndicates, human trafficking networks, and malicious state actors.
If bad actors operate entirely inside a decentralized ecosystem secured by fully homomorphic encryption and ZKPs, law enforcement literally cannot look inside. It doesn't matter if a judge issues a warrant. The raw data physically does not exist in a readable form anywhere on the server. The math prevents decryption.
It creates a space where accountability is technically impossible.
Exactly. When total absolute privacy is guaranteed by immutable mathematics rather than by flexible policy, who watches the watchers? How do we govern or police a digital society where absolute secrecy is a mathematical certainty?
That is the ultimate flip side of the coin. If you build an X-ray machine that is perfectly broken so it can't see the bones, you protect the patient's privacy, but you also lose the ability to see the tumor.
Exactly.
That is a profound, unresolved architectural question to leave on. Thank you to everyone for joining us on this incredibly extensive deep dive into the mechanics of 2026 data privacy.
Thanks for having me. This was a great discussion.
A massive shout out once again to our sponsors, CISOmarketplace.com and www.microsec.tools for making this deep analysis possible. Until next time, stay curious, keep questioning the blueprints, and we will see you on the next deep dive.